This research paper presents a novel approach to modernize Earth system models, ESMs, by translating them from Fortran to Python, JAX, leveraging large language models, LLMs, for code translation. The authors aim to make climate models more efficient, inclusive, and differentiable, enabling hybrid models that integrate machine learning methods. They demonstrate this concept through the translation of the photosynthesis model in the Community Land Model, CLM, of the Community Earth System Model, CESM. The proposed workflow involves isolating Fortran source code and dependencies, generating unit tests, and using these tests to iterate on the generated Python code. The translation process is facilitated by static analysis, code generation, and unit testing. The resulting Python versions include NumPy, Numba, SciPy, and JAX, with the JAX version requiring substantial modification from the LLM-generated code. The evaluation of the translated code reveals significant improvements in runtime efficiency, particularly with the JAX version, which achieves up to 100x faster runtimes using GPU parallelization. This increased efficiency can enable higher resolution simulations and the resolution of fine-scale processes. Moreover, the Python code is more readable and accessible for early career scientists, enhancing model development inclusivity. The use of JAX also enables automatic differentiation, a crucial feature for integrating machine learning methods into ESMs. This allows for hybrid models that can be optimized and updated in real time, enhancing both efficiency and precision. The authors provide open-source tools to address translation challenges, further facilitating the modernization of ESMs. This research highlights the potential of LLMs in accelerating the translation of legacy code to modern languages, thereby bridging the gap between complex research papers and concise, informative summaries for expert audiences. It demonstrates a path towards making climate models fast, inclusive, and differentiable, paving the way for future advancements in Earth system modeling. The research paper discusses the translation of a leaf-level photosynthesis module from Fortran to Python, leveraging tools like JAX for automatic differentiation and GPU parallelization. This component is part of the Community Land Model, CLM, which is a critical module in climate change modeling. The paper presents a comparison between different Python versions and the original Fortran version, demonstrating that JAX GPU was the fastest, followed by JAX CPU and Numba, with Fortran being 2 orders of magnitude slower. NumPy and SciPy were found to be the slowest. The study also explores parameter estimation for the maximum rate of carboxylation, VCmax, a key parameter in determining the CO-limited rate of assimilation. By employing gradient descent and uniform sampling methods, the paper shows that gradient descent can efficiently find optimal parameter settings, requiring fewer iterations and achieving a lower loss value compared to uniform sampling. This suggests that using ML methods such as stochastic gradient descent for efficient parameter tuning through automatic differentiation would be beneficial for future work in CLM. Challenges encountered during the translation process include poor Fortran generation quality, inaccurate unit tests, incorrect use of imported modules, and GPT-4 token limits. To scale up translation, the authors propose utilizing data flow and compiler representations for translation, incorporating logging to track function calls, and designing Copilot-style interfaces to support human translators. These advancements will further reduce manual work involved in translating and modernizing climate models. The paper concludes that migrating a full climate model from Fortran to Python is challenging due to dependencies and logical errors in code generation. However, translating individual components like leaf-level photosynthesis from Fortran to Python, JAX is feasible and valuable, paving the way for climate models to become differentiable, GPU, TPU-friendly, and more accessible to junior scientists. This could potentially lead to faster and more accurate models, accelerating progress in climate change modeling and adaptation. This paper explores the intersection of climate modeling and machine learning, focusing on enhancing climate model parametrizations through deep learning techniques. The authors discuss various challenges in climate modeling, such as structural biases and limitations in representing subgrid processes, which are crucial for accurate climate predictions. They propose leveraging advanced machine learning algorithms to improve these parametrizations, particularly with the use of JAX, a Python library that allows for automatic differentiation and JIT compilation. The paper highlights several key references that support this approach, including works by Gentine et al. 2018, and Yuval and O'Gorman, 2020, who demonstrated the potential of deep learning in enhancing climate model accuracy. It also references research on the development of high-order computational fluid dynamics solvers for compressible two-phase flows, Bayes-Ginn et al. 2023, and the importance of automatic differentiation in improving model efficiency, Margosian, 2019. Moreover, the authors emphasize the role of large language models like GPT-4, Sanderson, 2023, in generating code snippets for specific tasks, which could potentially aid in creating more efficient climate models. They also cite studies on code translation, Weiss et al., 2022, Safraniak et al., 2023, and its implications for bridging the gap between different programming languages used in climate modeling. The paper further discusses the need for end-to-end differentiable and GPU-accelerated cosmology libraries, Margosian, 2019, as well as the importance of tuning climate models to eliminate structural biases, Williamson et al., 2015. It concludes by emphasizing the potential of integrating machine learning techniques into climate modeling to enhance predictive capabilities and improve our understanding of complex climate phenomena. This research paper discusses the development of a semi-automated translation method for converting Fortran code to Python, utilizing large language models, LLMs, to assist in the translation process. The method involves two primary steps: dividing the codebase into manageable chunks using static analysis and then translating each chunk from Fortran to Python through the use of unit tests and iterative language model generations. To initiate the process, the codebase is divided into smaller, testable units such as functions, types, or subroutines. A dependency graph is generated to determine the order of translation, ensuring that functions are translated in the correct order based on their dependencies. This is achieved by first parsing the code to identify units and their references, and then forming a dependency graph based on these references. The translation process uses a variety of prompts tailored to different tasks, including translating Fortran to Python, writing Fortran unit tests, and writing Python unit tests. These prompts are designed to elicit specific responses from the LLM, which can then be used to generate the desired output. The GPT-4 chat completion API is utilized for this purpose, accepting prompts in the form of chat messages. The paper also discusses the importance of creating a balanced approach for parsing code and finding references within the project. This can be achieved through the use of parsing tools like fparser, which can return a syntax tree from the original source code, or by employing the Language Server Protocol, LSP, used in text editors like VS Code for features such as go-to-definition. The latter approach is considered more effective due to its ability to provide a balanced solution for parsing code and finding references. Overall, this research presents a novel method for translating Fortran code to Python, leveraging the capabilities of LLMs to assist in the process. By dividing the codebase into manageable chunks, generating a dependency graph to determine the order of translation, and utilizing tailored prompts to elicit specific responses from the LLM, the authors demonstrate a promising approach for automating the translation of legacy code. The proposed approach for translating Fortran code to Python involves three main steps: divide, conquer, and combine. In the divide step, the codebase is chunked into individual units using a parsing tool and tracing references. This process is visualized in Figure 5, where each unit's dependencies are formed through a dependency graph. To ensure these units function correctly, they must be unit tested. A logging tool, such as kgen, can log inputs and outputs for a Fortran function within the original code, generating unit tests. Alternatively, GPT-4 can be used to generate unit tests based on its knowledge, utilizing prompts from Table 1. In the conquer step, an iterative approach to code generation is implemented. This process takes a chunk of Fortran code along with corresponding unit tests and generates Python code and unit tests. A Docker image is created to run the tests automatically. If any test cases fail, the test output is passed back into the GPT-4 API, which returns revised code. This process is depicted in Figure 1. Combining the divide and conquer steps, a module was created for identifying dependencies between symbols in Fortran source code, as well as a command line interface for generating and iteratively updating a Python translation. To demonstrate the proof of concept, runtime and parameter estimation for the leaf-level photosynthesis module from the community land model were conducted, leveraging the power of automatic differentiation for model parameter tuning. The provided source code and unit tests are for a function that calculates the length of daylight given latitude and solar declination. The function is implemented in both Fortran and Python, with corresponding unit tests for each language. The Fortran version of the function, named daylength, calculates the length of daylight in seconds. It first checks if the latitude or declination angles are too close to the pole, which could cause computational issues due to the cosine function. If this is the case, it returns nan, not a number. For valid inputs, it computes the daylight length using trigonometric functions and returns the result in seconds. The Python version of the function also calculates the daylight length but uses NumPy's arctan2 function to avoid division by 0. It ensures that the input latitude and declination are within valid ranges and returns nan for invalid inputs. The function then computes the daylight length using trigonometric functions and returns the result in seconds. Both versions include unit tests to verify the correctness of the function. These tests check standard points, points near the poles, and edge cases where the function might fail due to numerical instability. They also test error handling for invalid inputs. In addition to the daylight length function, there is a class named bounds in the Python code. This class has a method called compute_max_daylength, which computes the maximum daylight length for each grid cell in a given range of latitudes and declinations. The table provided shows sample outputs from a translation run on the day length function in the community land model. It includes the original Fortran code, original Fortran unit tests, generated Python code, and generated Python unit tests.